Hello, ladies and gentlemen. Root Beer here, and I want to thank you for joining me as we finish off our 2012 Cayley paper. The digits of the positive integer n have no nines, four eights, exactly three sevens, and two sixes, and we've got some other numbers. The sum of the digits is 104. The sum of the digits of 2n is just 100. The number of times that the digit 5 occurs in n is... Okay, this is interesting. So, how are the digits, the sum of the digits of n related to the sum of the digits of twice n? Let's think about this for a moment. Let's just look at some simple things. They mention an 8. The sum of the digits of 8 is 8, but the sum of the digits of 2 times 8 is 16, so that'd be 7. One of the digits there is 1 plus 6, 7. What if I had something like 18? I know the sum of the digits there is 9. And we get 36 is twice 18. The sum of the digits there is 9. Now, is there any connection? Okay. Well, when we add the digits, we just care, what's in the tens column, what's in the ones column. Now, when I double 8, I get 16, and then when I double the 1 here, I get a 20. If I look there, 0 plus 2 plus 1 plus 6 is 9, because the 1 and the 2 combine to give me 3. Right? So if you look at it like this, it looks like you just need to double each of those digits and add things up. Okay? That way, when we make our number n, it doesn't actually matter where the 8s and the 7s are, and the 6s, I think, and some 5s, and maybe some other stuff. Okay? So if we take a look at 81, it's got the same sum of digits. And if I double 81, I get 162, and that also has a sum of 9. And we could keep trying this out to, experiment. 73, sum of the digits is 10. Double it, I get 146, and get the sum of the digits there is 11. 37, sum of the digits is 10. If I double that, I get 4, carry the 1, I get 47. It's kind of interesting. I never thought about it like that. But it looks like the sum of the digits doesn't change when you double. I don't think the same thing is true when you triple, because you might be able to get into some bad situations with too many things carrying. But the fact that we have no 9s, I think, is going to be useful to us. Okay? So let's think about this. 4 8s, 3 7s, 2 6s, that's 32, 21, 12, that's 65. So that's that's going to be 39. So 39's left over. Okay? So we need to make 39 up with some 4s and some 5s and some 2s and stuff like that. And if we take a look at the multiple choice answers, we can see we get at most 4 5s is what they're saying is possible. If for some reason we do a whole bunch of work and we see, we must have 5 5s or 6 5s, or 7 5s, we've done something wrong. Okay? Now, these 4 8s contribute a total of 28 to the sum of 2n. These 3 7s, 1 plus 4, give me 15 being contributed. And these 2 6s, well, 6 times 2 is 12, gives me 6. So 28, 15, and 6. So we've already got 21, 28, 49 out of 100 accounted for. So that means 51 is left to go. Okay? Now, think about these other digits. 5, suppose we've got K5s. That would be K5 plus 65 plus some other stuff gives me 104. But each 5, when you double it, you get 10, each 5 should really just be adding 1 for the overall sum of digits. And again, if we're a little unsure, we can think about this. 8 twice 8 gave us a sum of 7. Okay, 1 plus 6. If I do 5, 8, 5, I theorize I should get a sum of 9. And if we want to, just really quickly grab our calculator, 585 times 2, 1170. It does have a sum of 9. So every time we've got a 5, we sort of add on to what we previously. So every 5 should add on 1. Okay? Now, where were we going with this? So that contributes K plus the other 49. Okay? Now, if I have 4s up here, 4s contribute 8. Maybe I have A4s, well, I'll have A8s. If I have B3s, then I'll have 6 Bs being added on here. How many 2s? Well, if I have C2s, I'll get C times 4, and then if I have some number of 1s, right? So we get an expression like this. So, well, where can we go from here? I suppose one thing we could do is to maybe guess and check. 8D plus, I'm just copying it again. Sorry, it was 8A, wasn't it? 8A. A is the number of 4s. B is the number of 3s. 100 here. 5 Ks. So 4 A's, 3 B's, 2 C, and D. Now I notice here these parts are double each other, which is kind of interesting. So if I were to double 104, multiply everything here by 2, I don't actually need to work out individually how many 1s and 2s and such we've got. Double 65 is 130. Now we get 208 over here. So what I can do is I could take, I can subtract these two. This part will all cancel out. 10K minus K will be 9K. 130 minus 49 will be 81. And 208 minus 100 will be 108. Subtract 81 from both sides, and I'll get 9K is going to be 18. And I can see that I must have 2 5s. That's the only way to deal with it. Okay? And this is much faster when we notice that, oh, the 4s, 3s, 2s, they just double. So we should just double. It's a lot easier than guessing, checking our way to, oh, well, maybe they've got 1 4 and 3 3s and trying to find something that way. Because it doesn't matter. Those go away, and we can easily determine the number of 5s. And if they had told us the number of 5s but didn't tell us the number of 6s, we probably could have done the same thing too. But there we go. We get our answer of 2. Comes out with a nice little algebra trick there at the end. And so C ends our Cayley paper. So if you're looking for more Cayleys, more grade 10 Cayley papers, feel free to browse around. I have plenty. I've also got Galois, which is a grade 10 written paper. And if you're looking for something a bit more challenging, the Fermat paper is a multiple choice. It's got 25 questions, but it's aimed at grade 11. Okay? Thank you guys so much for watching, and I'll see you for more math in the future. Take care.